We write V is equal to Rx, where x is equal to I, j, and k. And we say that V is generated by x. V is generated by I, j, and k. Now let's come to the same concept in a bit more general perspective. Let R be a ring with identity and M be left R module. Let X be a non-empty subset of M. Then we define a linear combination of X as follows. What we do is we take each element of X and multiply with an element of the ring R, which we call scalars, and take summation over all the elements of X. Let's call it alpha. Note that this is summation and the set X may have infinite many elements, and you know that in general we cannot add infinite many real numbers or infinite many elements. We can do that in very special cases. You have studied these cases when you are studying infinite series, but in general we have to be very careful when we talk about sum of infinite many elements. So for that reason we put a condition on these scalars ax, where all but a finite many ax are 0. So we are saying that as far as these scalars ax are concerned, only finite many ax will be non-zero, all other will be 0. So when finite many are non-zero, then this summation consists of sum of finite many elements, and then this is well defined. So this is definition of linear combination. Secondly, let's take set of all these linear combinations and prove following proposition. Let R be a ring with identity and M be left R module, let X be a non-empty subset of M. Then the set of all such linear combinations, let's denote it by capital N. Capital N is equal to alpha, such that alpha is equal to sigma x belonging to x, ax, x, where ax belong to the ring R, and all but a finite many, but a finite many ax are 0. So n is set of linear combinations of elements of x. We have to prove that this n is submodule of M, is submodule of M. So let's prove this thing. So let's have the proof. Let me write this n again. We have n is equal to alpha, such that alpha is linear combination sigma x belong to x, axx, where ax is ax are elements of ring, and all but a finite many, ax are 0. This is a very important sentence which we use in mathematics. All but a finite many ax are 0, which means that only finite many scalars are non-zero. All the other values of ax are 0. So this is n. In order to prove that n is submodule of M, we have three conditions. Number one, we shall prove that n is non-empty. Secondly, n is closed under addition. And thirdly, n is closed under scalar multiplication. So first of all, we note that zero multiplied with x, sigma x belong to x, this summation is equal to 0, and this particular element belongs to n, therefore n is non-empty. Therefore n is non-empty. So first condition is satisfied. Let's come to second condition. Let alpha and beta be two elements of n. Then alpha is linear combination of elements of capital X, then alpha is equal to sigma x belong to X, AX, X, where AX belong to R, and that condition all but a finite many AX are 0 with that condition, and beta is equal to sigma x belonging to X, BXX, where Bx belong to R, and that particular condition is valid again. All but a finite many Bx are 0. We define, or we can simply add alpha and beta with each other. Alpha plus beta is equal to sigma x belonging to X, AX plus BX multiplied with X externally, and we know that AX plus BX, sum of these two scalars belong to R again. Therefore, alpha plus beta is again a linear combination of elements of X. Therefore, alpha plus beta belong to N. And this can be seen very easily that since finite many AX are non-zero, finite many BX are non-zero, therefore finite many AX plus BX are non-zero. It is just obvious. So, therefore, N is closed under addition. Secondly, we come to scalar multiplication. Now let alpha belong to N and A is a scalar element, or A is an element of the ring R. Then, by definition, alpha is equal to linear combination of elements of X, X belonging to X, AX, X, and therefore if we multiply alpha with A from left hand side, A alpha is equal to A multiplied with this linear combination X belonging to X, AXX, and this is equal to sigma X belonging to X, A into AX X, and this is equal to sigma X belonging to X, A into AX X, and therefore A alpha also belongs to N, because scalar element A multiplied with scalar element X belong to R, and that condition that only finite many of A into AX are 0 is just obvious. Therefore, N is closed. n is closed under scalar multiplication. And hence we have proved that n is submodule of m. So this completes the proof. Let's have a note. We write this particular n as r multiplied with x and say that n is submodule generated by x. And other note, it may happen that set of all the linear combinations of x, which is Rx, becomes exactly equal to the module m. Then in this case, m is called module generated by x. And let's have another note. If m is equal to Rx, where x is subset of m and x is finite, there are finite many elements in x, then m is called finitely generated module. And let's recall that we had V as set of three-dimensional vectors, and we had x as I, j, and k, which is a finite set, and this is subset of V. This is finite subset of V. Further, we have noted that V is equal to Rx. Therefore, V is the set of all vectors in the space. So therefore, V is finitely generated module. V is finitely generated module. Now let's come to another concept. We have learned a lot about this concept in group theory and in ring theory. And you remember that if we are given a group G and N is a normal subgroup of G, then G factor N is called factor group or quotient group. Similarly, if R is a ring and I is a two-sided ideal of the ring R, then R factor I is also a ring, and this is called factor ring or quotient ring. We have same concept in case of modules as well. Quotient module, or we may say it factor module. Quotient module. Quotient module. So let R be a ring with identity. R be a ring with identity. And M be a left R module. Let M be a left R module. Let N be submodule of M. We know that in particular M is an abelian group under addition, and N being submodule of M, N is a subgroup of M, and since M is abelian group, therefore N is normal subgroup of M. Then it is obvious that N is normal subgroup of M, and therefore we have quotient group which is M factor N, and this consists of cosets, left cosets or right cosets, whatever you like, we will write left cosets. M factor N is equal to X plus N such that X belong to M. And we know that addition in this case is given as X1 plus N plus X2 plus N is equal to X1 plus X2 plus N. And you know that from group theory. So this is addition of left cosets. Further, additive identity. Additive identity, or you may call it 0 of m factor n is given by n. N is additive identity of m factor n, or n is 0 of m factor n. Now let's come to the proposition. Let R be a ring with identity. Let R be a ring with identity and M be a left R module. Let N be submodule of M. Be submodule of M. Then the factor group M factor N. M factor N. N is normal subgroup of M. So M factor N is defined as factor group. Then the factor group M factor N is also a module. So we have to prove that M factor N is also a module. Let's prove that. First of all, first condition. For module, we have to prove two sets of conditions. First one is module has to be an abelian group. And secondly, scalar multiplication, and then those four conditions we already know. So as far as M factor N being abelian group is obvious because M is abelian group. So first of all, we know that N is normal subgroup of M because M is abelian. M is abelian group. So N is normal subgroup of M. Therefore, M factor N is defined further. M factor N is abelian group because M is abelian group. Since M is abelian group, so M factor N is also an abelian group. So our first condition is satisfied very simply. Now we come to scalar multiplication. Let's recall. We recall above things we have just noted above. We recall that x1 plus n plus x2 plus n is defined as x1 plus x2 plus n. This is for all x1 plus n and x2 plus n belonging to m factor n. So we just recall the addition in m factor n. Further, capital N is zero element of m factor n, is additive identity in m factor n. So first condition is very simply verified. Now we come to scalar multiplication. So we have to define scalar multiplication or external law of composition. We define scalar multiplication as follows. Scalar multiplication as follows. As follows. Let A be a scalar. A belong to the ring R and x plus n be an element of m factor n. Then we define A scalarly multiplied with x plus n is equal to A scalarly multiplied with x and then its left coset with n. So this is the way we define scalar multiplication. A into x plus n is equal to ax plus n. Now we shall prove that this scalar multiplication is well defined, and then we will verify the four conditions of being a module. First of all, we shall prove that this scalar multiplication is well defined. Is well defined. For this, suppose these two cosets x1 plus n and x2 plus n are equal. Suppose these two cosets are equal, then x1 minus x2 plus n is equal to n. And recall from group theory that if this happens, then x1 minus x2 belong to n. This is concept from group theory, and therefore since n is some module, therefore a into x1 minus x2 belong to n, because where a belong to R, further n is some module. So for that reason, if x1 minus x2 belong to n, then if you multiply x1 minus x2 with any scalar, this result will belong to n, and therefore ax1 minus ax2 belong to n. Again, from same concept from group theory which we have used earlier, since this is an element of this group subgroup n, therefore its coset with n will be equal to n. So therefore ax1 minus ax2 plus n is equal to n, and therefore ax1 plus n is equal to ax2 plus n, and therefore a multiplied with x1 plus n is equal to a multiplied with x2 plus n. So if x1 plus n is equal to x2 plus n, then a into x1 plus n is equal to a into x2 plus n, where a is element of the ring R. So therefore scalar multiplication we have defined above is well defined. So therefore scalar multiplication is well defined. Is well defined. Now we come to conditions for m factor n being a module. So for conditions being a module, we have to see that it was number 2, we come to number 3. Number 1, no, number 2, number 3. To see that m factor n is left R module, we need to verify that. To see that m factor n is left R module, we need to verify that number 1, we need to verify that number 1, we have to verify that a plus b multiplied with x plus n is equal to a multiplied with x plus n plus b multiplied with x plus n. Secondly, we need to prove that a multiplied with x1 plus n plus x2 plus n is equal to a scalarly multiplied with x1 plus n plus a scalarly multiplied with x2 plus n. And then third condition is a and b multiplied with each other, then multiplied with x plus n must be equal to a multiplied with b multiplied with x plus n. And then fourth condition is quite simple, and that is 1 multiplied with x plus n is equal to x plus n. So let's see the proofs. Proof of 1. Proof of 1. Let's see the left hand side. Left hand side is equal to a plus b scalarly multiplied with x plus n. And by definition of scalar multiplication, this is equal to a plus b multiplied with x and then plus n. And this is equal to a multiplied with x plus b multiplied with x and then plus n. And this is equal to, by definition of addition of cosets, this is equal to ax plus n and then plus bx plus n. And then by our definition of scalar multiplication, which we have defined above, this is equal to a multiplied with x plus n and then plus this is equal to b multiplied with x plus n, and this is equal to right hand side, the same thing, right hand side, this is equal to right hand side. So first condition is verified. We come to proof of 2. For this, left hand side is equal to a multiplied with x1 plus n plus x2 plus n, and this is equal to a multiplied with x1 plus n plus x2 plus n. By definition of addition of cosets, sum of these two cosets is equal to x1 plus x2 and then plus n, and this is equal to, now this is scalar, so by our definition of scalar multiplication, this is equal to a multiplied with x1 plus x2 and then plus n, and this is equal to a into x1 plus x2 is equal to a x1 plus a x2, because of definition of module, m is module, and this is equal to a x1 plus a x2 plus n. Then again, using definition of sum of cosets, this can be written as ax1 plus n and then plus ax2 plus n, and this is equal to ax1 plus n is equal to a multiplied with x1 plus n plus a multiplied with x2 plus n, and you can see that this is the same thing right hand side, so this is equal to right hand side. We come to proof of 3. Proof of 3. Again, left hand side is equal to AB multiplied with x plus n, left hand side. Now by definition of scalar multiplication, we have just defined, this is equal to AB multiplied with x and then plus n, and this is equal to AB multiplied with x is equal to A multiplied with bx. This is condition of M being left R module, and then plus n. And this is equal to A into bx plus n can be, by using definition of scalar multiplication, this can be written as A multiplied with bx plus n, and this is equal to A multiplied with bx plus n can be written as b into x plus n, and this is right hand side, this one, this is right hand side again. And the fourth condition is very simple. Anyway, let's write that as well. So proof of 4. So left hand side is equal to 1 multiplied with x plus n. By our definition of scalar multiplication, this is 1 multiplied with x and then plus n. And 1 multiplied with x is equal to x. So this is x plus n, and this is equal to right hand side. Therefore, all the conditions are verified. All the conditions are proved. Therefore, m factor n, which is in fact quotient group, n is subgroup of m, and m factor n is quotient group. This is a module as well. Therefore, this is left R module as well. So this completes the proof. Thank you very much.